sklearn base classifier mixin. Description: Classifier mixin is a base class in scikit-learn sklearn that provides a common interface for classification algorithms. It defines the basic methods that all classifiers in sklearn should implement. This ensures consistency and allows for seamless integration with other sklearn components. Inputs. X. The input data. Typically a 2D array where each row represents a data point and each column represents a feature. Y. The target labels. A 1D array containing the true class labels for each data point. Outputs. Predictions. A 1D array containing the predicted class labels for the input data. Probabilities. Optional. A 2D array where each row represents a data point and each column represents the probability of belonging to a specific class. Steps. Training. The classifier is trained on the input data X and target labels Y. This step involves learning the underlying patterns and relationships between features and classes. Prediction. The trained classifier is used to predict the class labels for new unseen data. Metrics. Accuracy. The proportion of correctly classified instances. Precision. The proportion of correctly predicted positive instances among all instances predicted as positive. Recall. The proportion of correctly predicted positive instances among all actual positive instances. F1 score. The harmonic mean of precision and recall. Visualization plots. Confusion matrix. A visual representation of the classification results, showing the number of true positives, true negatives, false positives, and false negatives. ROC curve. A plot showing the trade-off between true positive rate sensitivity and false positive rate 1 specificity for different classification thresholds. Precision recall curve. A plot showing the trade-off between precision and recall for different classification thresholds. Fine-tune parameters. Regularization strength controls the amount of penalty applied to model complexity, helping to prevent overfitting. Number of estimators for ensemble methods like random forests. This parameter determines the number of individual models combined. Learning rate for gradient-based algorithms. This parameter controls the step size during optimization. Uncertainty methods. Confidence scores. Some classifiers provide confidence scores for each prediction, indicating the classifier's level of certainty about the predicted class. Bayesian methods. Approaches like Bayesian classification can provide a probabilistic interpretation of the predictions, incorporating uncertainty. Challenges and fixes. Challenge 1. Overfitting. The model may perform well on the training data but poorly on unseen data. Sample use case. A model trained on a small dataset with many features may overfit to the specific examples in the training set. Fixes. Regularization. Add penalties to the model complexity to discourage overfitting. Cross-validation. Split the data into training and validation sets to assess model performance on unseen data. Challenge 2. Class imbalance. When one class has significantly more instances than others, the model may bias towards the majority class. Sample use case. In fraud detection, the number of fraudulent transactions is usually much smaller than legitimate transactions. Fixes. Oversampling duplicate instances of the minority class to balance the dataset. Undersampling. Remove instances from the majority class to balance the dataset. Cost-sensitive learning. Assign different costs to misclassifications depending on the class, making the model more sensitive to the minority class. Challenge 3. Data dimensionality. High-dimensional datasets can lead to computational challenges and potentially overfitting. Sample use case. Text data often has a very high number of features words. Fixes. Feature selection. Select a subset of the most relevant features. Dimensionality reduction: apply techniques like PCA to reduce the number of dimensions while preserving important information. Challenge 4: missing values. Incomplete data can affect model performance. Sample use case data may have missing values due to data collection errors or other reasons. Fixes: imputation: fill missing values with estimated values based on available data. Model-based imputation: use a model to predict the missing values.